So I'm going to apologize up front because I was up too late last night talking, so I'm losing my voice. And then I was sitting in Connor's talk and not feeling well, so I ran up to my room to take a quick COVID test, and I'm negative. So that's good. But if I'm sniffling through this talk, you'll know why. So that aside, as he said, yeah, I'm a senior principal scientist at Adobe, and I've had the pleasure over the last year of reforming Adobe Software Technology Lab, which is a group I ran about a decade ago. And I've got David Abrahams on my team. David Sankel is also on my team, if you know David from Bloomberg. He's at the conference, but he's sequestered in his room because the first morning he's one of the people who tested positive for COVID. So he's kind of stuck in Toronto for a little while. And then somebody who I hope you guys will get to meet probably at the next conference. He couldn't get his passport straightened out in time, but his name is Nick DeMarco. And he's not well known in the C++ community. He was on the C++ standards committee briefly, and I think will be more involved again, and I'm hoping to get him to conferences and speak. He's a sharp individual. Adobe is hiring. In fact, David Sankel pulled off a miracle. Mike was just informed me Dave's been sitting up in his room. He managed to get Adobe to sponsor this conference. So we're kind of a last-minute sponsor to help us out. So I think that's great. The QR code there will take you to a website that talks about C++ and what's going on with C++ at Adobe. And I think last time David ran the numbers, we have something like 900 open positions that mention C++. So we are hiring. So let's kind of step through into the future a little bit here. So closing keynotes are really challenging, right? If I had Kate's slot, if I were giving an opening keynote, the goal of an opening keynote is to spark discussion, to give everybody in the audience something that they can talk about with each other during the conference, kind of an icebreaker. That's what you want to do in an opening keynote. And I think Kate did a fantastic job in her opening keynote. It sparked a lot of conversation. I've had many conversations with various people at the conference who have asked, what do you think of what Kate said, and do you have any advice about being a good programmer, and just lots of thoughts that went around. So I did want to share one thought that I had that came up, which is Kate gave her list of what makes you a good programmer. Not everybody who's a good programmer, I think, is good at all those things on the list. I'm not. I will tell you that. What I am good at is finding people who are good at the things that I'm weak at and working with them. So my Achilles heel is, Kate said, a good programmer finishes things. I have a really hard time finishing things. And it's not because I get bored with it and I go away. It's because I do an infinite descent. For anything that I start on, I find something interesting inside of that, and I find something interesting inside of that, and I keep going deeper and deeper. And if you just let me, I would spend 20 years on any problem until I got it down to piano axioms. That's just what I do, okay? So I try to find people who are good at getting things back on task and cutting off tangents and getting things moving. So that's just a tip. If you have a weak area, find people that complement you, work with them. If they do complement you, it probably means they think differently. So get good at listening to them and giving them space to do their thing, to do what they do well, because that will make you a better person. So I just wanted to give that little short piece of advice. To get back on topic, we were talking about closing keynotes. So a closing keynote's purpose is to inspire and unite everyone so that you guys go away and now you're not collective anymore, you're not at the conference, you have something to think about, something to mull over. Hopefully something to inspire you, to get you excited, to carry you through the next year, and then hopefully you come back and you're here and you join us again. The problem is I really fear that this keynote's going to fail. Because I think for some of you, this keynote is going to just bring despair. And so I'm going to apologize for that up front. This talk is a follow-up talk to a talk I gave now just over 10 years ago at C++ Now in Aspen. And at that time, 10 years ago, so we're looking at 2012, C++ 11 had just rolled out and was starting to get adopted. And so I titled the talk at that time, C++ Now What? Okay, we're done with C++ 11. Where is C++ going to go next? And if you see, there's some overlap between kind of my title and Chandler's talk and his title. That was completely unplanned. At the time that I was planning this talk, I was not aware of Carbon. So just a coincidence in how these things lined up. So the title of this talk is The Tragedy of C++, Acts 1 and 2. 3 acts, if you're curious as to how many acts I think are in this play. In this story, C++ is our protagonist. Okay? This is who we're following. Now, I'm not going to go through the whole history of C++. C++ was born as a marriage between Simula and C. Bjarne Stroustrup has written 3 Hopple papers, which is pretty amazing, that cover C++'s evolution all the way from 1979 through 2020. There's also Design and Evolution of C++, which is a great book that will give you lots of insights into how and why C++ evolved the way it did. So these are good references, but this is not important to our story. This is not what we're concerned with for C++ today. What we're concerned with is where has C++ arrived to? So what is C++ good at? Let's look at some of the obvious stuff. Performance. If you don't care about performance, you probably don't care about C++, and you're probably not in this room. That's probably the most obvious reason why people go and reach for C++. Platform support is also very important, right? C++ is pretty much ubiquitous. It's hard to find a device that cannot run C++, and do so relatively easily and with good support. Tooling around that, we have multiple compilers, we have debuggers, we have profilers, we have IDEs, we have memory tracers, we have formatters, we have Clang Tidy to go rewrite your code and make changes. There is a lot of infrastructure around tooling around C++. It's not as great in some areas. We don't have great package management, but in general, we have tooling pretty well in hand. C++ is high level. This is one of the things that distinguishes on this list C++ from C, right? If you're not concerned with building abstractions, you're probably just going to write in C and not bother learning this much more complex language. And available libraries. There's a lot available for C++. We tend to kind of narrow it down to just the standard library or just the standard library in Boost. But if you look around, there's a lot of high quality, very capable libraries available in C++, or at the very least available to C++. Some of the things that maybe aren't so obvious, I think this one used to be very obvious, but C interop. You don't have to go through like an extra thunk layer to call C. For the most part, you can just include a C header file in your C++ code and call it, right? Usually that means the header file has an extern C, curly brace, end brace. If you're running in C++, a couple conditionals. But almost every C header file these days has those in there just because C++ is so ubiquitous. So C interop is a key reason for C success and why we continue to use it, because if you ever look at the language stats, C is still an incredibly popular language. It still typically dominates as number one. So there's a lot of quality libraries out there that are written in C also, not C++, and we can call them all. Another maybe not so obvious reason why companies and individuals tend to use C++ is because of the specification, right? A lot of languages are not particularly well specified, right? And it's not just that there's a specification out there so you can look up so that you know how it's supposed to run. There are multiple vendors that are shipping compilers that are written to that specification, and now you have a good way to know, is this a bug in this compiler or not? Does it comply to the specification or not? Another piece of this is the standardization process for the specification. Everybody in every country has an opportunity to contribute to the standard. It's not a perfect system. It's a very political system. But speaking as somebody from at Adobe, that's important. It's important that we have an opportunity to have our say and that we have a forum within which we can express what our problems are and what our pain points are. So we already went through those. Another thing that might not be so obvious is the community around C++. There are some really brilliant people working in this community. And over my ridiculously long career, I think probably only Kate in this room has me beat. Well, no, that's not true. There's a couple other people in this room that have me beat. But I've had the pleasure of meeting many of these people. I've had the pleasure of working with some absolutely great individuals. And I have the opportunity to come to conferences like this and talk to just some amazing people. So that's huge with C++. And it's been amazing just since Dave created BoostCon. I mean, before BoostCon, there was like one C++ conference that happened 1 year in Las Vegas that I spoke at called C++ World. And then Dave created BoostCon, and then John created CppCon, if I get the ordering right, and then BoostCon became C++ Now, and then all of a sudden it exploded, right? This community is amazing. I think both Kate and I share the fact that we've had the opportunity, and Guy also, and a few other people in this room, we've had the opportunity to speak all over the world to lots of amazing people. I've met so many people in this community. And they're generally helpful. Junior, a new C++ first-timer at the conference here, asked me the other day, what's a tip that you would give to somebody first starting out? And one of my tips was don't be afraid to ask people. And I don't mean that just in person. I've sent emails to people who I've never met, who wrote a spec or wrote a paper or something, and I thought, what I'm working on, they might know the answer. Sometimes I don't get a response, really rarely. I've never gotten a negative response. And every response that I've gotten has been, hey, thanks for asking. Here's what I think about it. And some of those turn into very long conversations. Right? So don't be afraid to reach out to people. I occasionally get emails. People send me a thing, hey, Sean, how would I do this? Right? I will do my best to answer those. I get a ridiculous amount of emails, so if I don't answer you, if I'm the person who didn't answer, don't ever take that as a negative response. Send it again, because then it'll be at the top of my inbox, and I'll see it again. The community is active, right? As I already mentioned, it's not just the conferences, it's the user group meetings, it's Twitter, it's people posting on blogs. There's just an amazing amount of energy. Another thing that I think makes C++ unique is the STL. And this is kind of odd in that, the STL now is old, right? And I think it was a landmark in programming, right? It changed the way people think. It took a long time. It is still kind of the best example of generic programming, of the fundamentals of generic programming. Other languages might have better mechanisms to express some of generic programming, but when you get to the combination of all of the STL algorithms and how well thought out they are and how well specified they are and the containers that go with them and the ability that you can just take a container and mix and match it with an algorithm and get high efficiency, that's unprecedented. And I think C++ is still out in front in this regard. Mutable value semantics. My colleague Dave has been working on a whole language called Val around this idea of mutable value semantics, but a language where when you create a user-defined type, it's not some heap allocated thing that got nude that you got a reference to, and if the thing is mutable, that means it's shared, a la JavaScript or Java or most of the other languages out there. The fact that you can create user-defined types that behave, for the most part, like an int is very unique to C++. And this is actually incredibly powerful for reasoning about your code, for reasoning about things locally. You know that if you have an object with value semantics, if you've got an STD vector, you've got the STD vector. They're, barring somebody else having taken a pointer to it, nobody else owns that thing. Nobody else should have a reference to it. It's yours. That's incredibly powerful. And that comes up to be incredibly powerful when you're trying to do concurrent programming, to reason about concurrent programming. So if I had to distill down C++, if I had to describe our old protagonist in just one phrase, this would be my tagline for C++. It's flexible abstraction and efficient by definition. And I think that efficient by definition is also very important, right? I said early on, performance is an obvious thing. But C++, for the most part, is not performance by optimization. It's performance by definition. And I sat in Bryce's talk, wonderful talk, Bryce, both of yours. I went to both of your talks. If anybody else went to Bryce's talk, he put up a piece of code and then showed, well, this looks okay, but this is the assembly that it generated. Black, big, huge amount out of assembly. And what he was talking about was trying to vectorize some algorithms. And then he said, but if we express it this way, we get this very tight code, which is pretty close to what you would write if you were using intrinsics and getting it down. And I think we have to be careful a little bit here in not losing sight of this efficient by definition feature of C++. As we try to grow C++ out and expand into better support for SIMD, better support for GPUs, we have to figure out how do we do that so that the optimizations are by definition. It's like a return value optimization was in the language for a long time, but you couldn't rely on it until it appeared in the specification. Then you knew, I can do this and it will not make a copy. It won't make a copy in a debug build, right? It will perform as I want it to perform, regardless of my compiler options, all the time, and I'm not going to hit surprises. And so as a community, I don't think we want to lose that. So this is the power in C++. Now this brings us to Act 2. Now that we know who C++ is, we've learned a bit about our protagonist. the health of C++. And this is where I pull in my talk from 10 years ago. My talk from 10 years ago, besides being called C++ Now What, there was a little colon and it said a vignette in 3 parts. And I tried to look at 3 areas where I thought C++ could do better. And that was a decade ago. So let's take a look at those 3 areas and see how C++ is doing today. So the first area was beauty. Now, the C++ standard. C++ 98 was 757 pages. We're now up to just over 1,800 pages. 523 of those pages are for the language and the support libraries. The rest of it is the remaining part of the libraries. We're getting close to 2,000 pages. That's a lot. It's starting to look like a phone book, right? And not a specification. That's too much for any individual to read and actually understand, right? The first time I got a copy of the C++ 98 spec, I actually read it cover to cover twice. I have read most of the later versions of the spec, but it's hard. It really is to get through. It's just too much. I gave this example. Sorry, I kind of scrolled away a little bit. Looking at this 10 years ago, I looked at one indicator of the complexity of the language is how hard it is to write stood pair. Okay? So if you look, we have most of stood pair right at the top here, right? It's just a struct of 2 types. It's a template because they can be any type. We got the first type, we got the second type, and then we got 2 members, first and second. And I'm not complaining about the ugly underscores here. I get that's for making sure that these are private symbols so that they don't collide with the user-defined macro. That's all fine. I don't care about the macronized namespace. And I went through this file and I stripped out all the legacy support. So this is stood pair as it is in libc, libc++, without all the conditionals for supporting, C++ 11 and 98 and going back. And like everything you need is right there, right? That's stood pair, okay? So C++ 20, that's 502 lines of code to represent a pair of 2 objects. And this doesn't even do everything that I want to do with the pair, okay? I don't have a way to use this pair and say, I want a stood pair, except I want the members to be named key and value, right? Because that would kind of be useful. I want a pair of ints, meaning I want them to behave as if they were integers, but since they're of the same type, I should be able to index into them with an index operator, right? I also shouldn't have to say pair int int. It should be just implied. If I say pair int, that means 2 ints, okay? I can't do that, but I have all of this code, okay? C++ 11 was 372 lines, so 10 years ago, that's where we were. C++ 98 was 62 lines, okay? And Alex used to complain that this was too much, that we needed to simplify, okay? So for a very long time, we've been looking at trying to simplify. Why is this an indicator of health? Because the standard library should be, for the most part, an example of how to write a good library, right? If it takes 502 lines to express a pair of 2 objects, and you're working on an application and you say, well, I want that, but I want to call them key and value, but I want all the same capabilities. What do? Copy and paste, right? You can't get around that. If you say, I'm dealing with points and coordinates, and they could be a pair of floats or a pair of ints or a pair of things like that, and I want them to interoperate with pair, you have to dig through here and say, well, what stuff is in here because there are 2 types that are different types, and what stuff is in here because 2 types that are same types, and it's going to take you a while to figure out what you want to do to get the same set of capabilities that are in stood pair, right? So this is a problem. This was a quote that I gave at the talk from 10 years ago. My phone rang one day, and I picked it up, and it was an engineer on the Photoshop team, and they said, could I have you take a look at something? We're getting an error that has something to do with R-value references and stood pair. Okay? And I said, sure. And they sent me this big, long, scrolling list. If you go back and you watch the old talk, I have it scrolling by. It's this error message that just like goes on forever. I don't have that old code, so I couldn't compile it to get the same error message back out. But so I went through the error message and was looking at what it was, and what it was is it had a map, and I think it was the value in the map was a bool, so it was a map of some, like a string to a bool or something like that, and they were trying to assign an int into the bool in the map, okay? And so I thought, well, clearly now this is C++20, we have concepts, which are supposed to fix our error messages, and we added a whole bunch of code to stood pair, so that's got to be fixed, right? No, it's not. So just trying to recreate the code, that's the error message I got back out. Okay. So it didn't help. You know, if you're a user who's just starting out, this isn't nice. You made a typo, you got a type of a variable wrong, and you just got spewed, right? Right. And the error at the bottom, well, to finish the story, the original reason for the error message, when we dug through it, we actually looked at the line of code, and it was assigning true to the bool, but that whole thing was saying that you were assigning an int to a bool. And the engineer was like, but how can that be? It's true to a bool. And I thought for a minute, and I said, do me a favor. Grep the Photoshop code base for pound define true equals 1. If you go back 10 years, they've all been cleaned out now, but there was a slide. There were 20 hits. The engineer who was asking this said, who would do that, right? Who would pound define true to 1? And I said, well, our code base is 30-something years old, and it predates bool. And there's this long pause, and the engineer said, oh my God, you're older than bits. So that was 10 years ago. So what is beauty, right? I think beauty has a strong relationship to correctness. It's a multifaceted thing. But if I had to define beauty of a programming language, I would say this. Beauty is the ease with which a language allows the expression of correct code. When you sit down and write code, how easy is it to write correct code? How confident are you that the code that you wrote is correct? Right? Are you confident because it compiled, or are you confident because you can look at it and you know that's good code? Right? That's what we need to strive for. How do we strive for beauty within our programming language? Right? So I want to talk just a little bit about correctness. I pulled this from a talk that I gave at C++ Now, but I thought it was worth going over here. The idea of program correctness follows from the ideas of design by contract, which go to Bertrand Myers, and if you go back through the history, you get into Hoare logic and things like that. If you're really interested in the history, go see my other talk. But for the most part, we can kind of distill this down to functions have preconditions, functions have postconditions, and so long as the postconditions satisfy the preconditions, those are just predicates, so long as those match up, then the code is correct. So a precondition is assertion that must be true before an operation. So if I write something like sort first last compare, then I've got a precondition that first to last is a valid range, implying that first is less than or equal to last. For all p in the range first to last, p has to be dereferenceable, right? That's a precondition. For all p, let v equal the set of values of star p. And then for all pairs, VA and VB, the compare function is a predicate establishing a strict weak order relation on that pair. Okay? So preconditions are not things, you can type a comment on them. If we had contracts, you could maybe make a little statement about them. But generally, you're going to really hope that your compiler isn't inserting runtime code to say, well, for all the pairs out of this million element things, let's see if they compare the same and generate a complete strict weak ordering relationship. Those are things that you have to prove while you're writing your code and hopefully document and write down. Now, the domain of an operation is the set of values that satisfy all these preconditions, right? So the domain of operation of sort is all the things that you can pass to sort that satisfy all of these preconditions. I bring that up because there has been a lot of confusion. I gave a talk a while ago about a warning stood find is broken. You can look it up. What a lot of people took out of that talk was that find doesn't work with nans. That wasn't the point of the talk. The talk was that within this standard, which we have now grown to 1,800 pages, the wording around the domain of operation has been all but stripped out of the standard. And in reality, Howard Hinton and I had a long discussion on this. We don't think that you can actually legally call sort according to the current C++ standard on floating point numbers, whether or not there's a nan in the sequence, okay? Because domain of operation was removed and it was weakened to the point that said that basically sort has to be total, okay? That for any two integers or for any two floating point values that you hand to the compare operation must be total and impose a strict weak ordering, and nan doesn't satisfy that, okay? And so within this specification that has grown to 1,800 pages, you see signs of rot, right? It's not as logically consistent as it was before. We are adding stuff and we are editing stuff and we're pulling things out, and nobody can hold nearly 2,000 pages in their head at one time, and we don't have a formal language verifying our specification. And so we're starting to see logical contradictions creep in to this specification. That's a problem. That makes it very hard to reason about a piece of code and prove a piece of code, right? Can I prove that my code is working correctly when I call sort if the standard technically doesn't let me call sort on floating point numbers, right? So, when preconditions are not satisfied, this is the case that causes a lot of confusion. What happens if you pass sort, last first? That's a bug. By definition, that's a defect in your code. An operation, if you don't satisfy the preconditions in C++, may lead to undefined behavior, right? I'll hold that comment for just a moment. The result may be unspecified. It may violate the class invariance. It may lead to program termination. Which brings us to safety, because there is a lot of talk these days, especially on the Standards Committee group, about safety and what safety is. And there's an unfortunate thing that Dave learned is that ISO has a definition of safety, which is more around workplace safety and has nothing to do with what we're talking about here. And so when you're talking about safety in programming and the person on the other end is worrying about writing C++ for cars, there's a lot of confusion because they're thinking, how do I write C++ code to guarantee my car doesn't crash? And that's not what we're talking about here, right? An operation is safe if it cannot lead to undefined behavior. That's to put the term of safety within the C++ realm. Either directly or indirectly, right? If you violate the preconditions on an operation, which may lead to undefined behavior, okay, then you could see that undefined behavior any place after that within the execution of your program, right? You can see this, right? You write off the end of an array, which is undefined behavior. You stomped a piece of memory. It could be a while before that comes back and bites you, okay? And that could be a real pain to debug. Right. So, and directly or indirectly, it's indirectly even if the subsequent operations, even if the operation, I don't know what that comment meant. But it's supposed to be, yeah, even if the subsequent preconditions are not violated is what that line is supposed to say. An operation may lead to undefined behavior, or an unsafe operation may lead to undefined behavior if preconditions are violated. Oh, sorry, we were defining safe. So an operation is safe if it cannot lead to undefined behavior directly or indirectly, even if the operation's preconditions are violated. So we say it's safe if it can't lead to undefined behavior, even if you call it wrong. An unsafe operation may lead to undefined behavior if its preconditions are violated, either directly or during subsequent operations, whether those operations are safe or not, right? So once you stepped on that landmine, something's going to blow up. Or not. It's not guaranteed. We refer to an operation that terminates on a precondition violation or has no preconditions as being strongly safe, okay? So why is that strongly safe? Because if you do make a mistake, either you can't make a mistake because it's got a wide open contract, or if you do make a mistake, it tells you right now, boom, you're dead, right? So that's an important property. So safety is about incorrect code and the scope of damage it may cause. It's the blast area. When we're talking about safety, we're assuming you're going to make mistakes. I mean, I've never made any, but I'm sure you guys do, right? Don't believe that. I've written a lot of bugs. So what we're talking about here is the blast radius, okay? How much damage can your application do? Errors are about correct code and recoverable situations. Okay? So you don't want to return an error on a precondition violation, right? You want to return an error when you cannot satisfy the contract even when the caller satisfies the preconditions. Turns out safety is a transitive property. What I mean by that is if the only thing you have within your language are safe operations, you can't build an unsafe one, right? So if there's no way to get to undefined behavior in your language, there's no way in your program to get to undefined behavior. Unfortunately, correctness is not transitive, right? If all of your operations are correct, that doesn't mean your program is correct. It's very unfortunate. If it were, just everything we wrote would be beautiful. Strong safety is also not transitive, right? Why? Because correctness isn't transitive. Okay. So what happens if I write a function and I've got a set of preconditions and I violate those preconditions and I'm on a safe system, so I'm not going to lead into undefined behavior? What that means is I get unspecified behavior. I'm outside of the contract. It's going to do something, possibly terminate, okay? But I'm outside of contract. So, safety bounds the behavior of our incorrect code. Strong safety with tight preconditions can assist with correctness by catching mistakes at runtime, right? So I frequently say I want narrow contracts, right? I really don't want C++ to define signed integer addition as being modulo 2. That removes undefined behavior. It's completely safe, but it's not strongly safe, and that's going to hide bugs. If it's undefined behavior, the compiler can legally insert a strongly safe check and terminate my app, okay? So I want to make sure that I have that capability. So safety can mask errors by providing consistent, if incorrect, results. Safety is also fundamentally at odds with efficiency. Right? We kind of hope that we can build a language which is both safe and efficient. We have languages like Rust, which are safe by default, and Swift, which is safe by default. And what that means is first, the compiler is going to do things like either checking integer overflow or making it not strongly safe, just plain safe. With modulo arithmetic, it's going to check bounds errors on memory accesses, things of that nature. And hopefully the language then provides some higher level constructs so you can do things like iterate an array and not have a check at every single position in that array. The language provides some guarantee to say it's efficient by definition. Kind of the worst case is when people wave their hands and say, the optimizer is going to take it out. Because maybe it will and maybe it won't. And that's the kind of thing that's going to bite me 2 weeks before a product goes out the door and somebody's stuck in a line of code, and now something that was heavily optimized runs horribly and we lost 15% in the application, and I'm digging through with a profiler trying to figure out why, right? We want the efficiency by definition. So just to kind of walk through the choices with integer overflow, I mentioned this before. So integer overflow in C++ is undefined behavior. There's reasons for that, right? The compiler can actually optimize accordingly for that. If the compiler, what happens here is the compiler can assume that two integers can't overflow, and so being able to make that assumption means it's able to analyze a code path and figure out, oh, if these two things can't overflow by definition, then I don't have to generate this code, and I don't have to put in that branch, and I don't have to go over there. But then if you actually do overflow, all that code the compiler ripped out is going to give you really surprising results, right? If you're trying to check for overflow by assuming it's modulo 2 overflow, the compiler is going to say, that code can't execute. Nope, we're just going right by. You can find amazing examples online from Godbolt where it's like a function that otherwise was not reachable is reachable because of undefined behavior with arithmetic. So defining overflow as modulo 2 arithmetic is safe, but as I said, it hides unintended overflow. And it also comes at an efficiency cost. It's not huge because every processor today that I know of, this is what the processor does. It does modulo 2 arithmetic on it, and so the compiler is not inserting any extra instructions to do the arithmetic, but it can't assume that the overflow doesn't happen, and so there are some optimizations that it gives up. Is that a good trade-off? Maybe. Maybe it's a good trade-off. Defining overflow as trapping would catch mistakes, right? But it also comes at the cost of on most processors, including x64 and ARM, of an additional check and then a trap instruction. And it would be really nice, and I've looked up online, people have, it wasn't my initial idea, people have been asking for this for more than a decade. It would be really nice if modern processors had an instruction set that trapped on overflow for integer arithmetic. So the compiler could just do the add and trap with no different instructions. The reason why they don't is because they don't have the instruction set space. If you think about all of the operations on integers of various sizes and all of the shift operations and everything that goes on there, that is a whole boatload of instructions, and they don't have space in their instruction space to do that. So it's a design decision. So the limits of safety, and I think this is important to understand. Within a safe, Turing-complete language, you can build an unsafe C machine. Okay? If you've got a Turing-complete language, you can build C. a C machine, and then you can compile C code or C++ code and execute it inside of that C machine. In which case, the damage of incorrect code is constrained, but only within the simulation, right? Otherwise, it is undefined behavior. You can stomp on your memory, you can do all sorts of nasty stuff. So at a very theoretical level, safety is isomorphic with a strong sandbox. Not from a usability standpoint, okay? But if you're looking at things about provable security, safety doesn't give you that. All that safety does is you know, if all of my operations are safe, if everything is guaranteed to be safe, all I really did was I put a box around the outside to contain the damage. Okay. See asm.js as an example, right? asm.js was JavaScript that you could execute. You could compile your C++ program with the mscriptum compiler, pre-WASM, into JavaScript, and it executed. And you had all the same undefined behaviors and all the same issues, but the limit of your scope was you could just take down that JavaScript worker. Because JavaScript itself is safe, and so you couldn't escape that sandbox. So years ago, I had an argument with James Gosling on this around Java. Java was brand new, and I'd gone to something where he was giving a talk. And I said, you know, you're building this whole virtual machine around Java. Why don't you instead work on the OS side and just build a sandbox? Because all of his stated goals were around security and containment. And I'm like, then build a sandbox, and then we'll just compile C++ code and dump it in the sandbox, and it'll be great. He didn't understand what I was saying. He was making counter arguments. At the time, I didn't understand what he was saying. When I reflected on it, he was really concerned, even though he talked about security and correctness, he was talking about security and correctness by helping the programmer get there, right? By catching your mistakes. So this is an important property. He wasn't looking at it from a, what if somebody wants to build a C machine and do nutty things within my environment? Okay? He wasn't looking at it, is this a provably secure environment? So he was looking at it from the ergonomic side. I didn't get that at the time. I don't think he got my argument. So that brings us to the third section here of Act 2, truth. Or I'm sorry, second section. We did beauty, this is truth. So these slides, all the slides with the gray background, these are pulled directly from my talk 10 years ago. So 10 years ago, this was how the gigaflops on a desktop machine were distributed. That's your GPU. And 10 years ago, this is how you would access it. OpenGL, OpenCL, CUDA, Direct Compute, C++ AMP was a thing then. I think it's pretty much dead now. DirectX. OpenGL and OpenCL, unfortunately, are mostly dead now too. These are your vectorization intrinsics, right? You can get to those maybe through auto vectorization, at least a little bit, good compiler, or through OpenCL at the time, supported auto vectorization. This is just your main CPU, all your cores. At the time, we had C++ 11 threads. That's about the only thing in C++ to get us there. TBB is a reference to Intel TBB. GCD is Apple's libdispatch, or OpenMP. Those were all technologies to help you get to the many cores. And if you're writing just straight C++ code, you were down in that 0.25%. That's how big that slice is. That's how much of the gigaflops on that machine you were able to utilize. Okay. Now, we're now 10 years later. I was not able to create a new graph like this, partially because the notion, now we talk about teraflops. A typical GPU you will find, kind of mid to higher range GPU, is capable of something like 20 teraflops. So almost 10x what's capable here. As far as I can tell, CPUs have maybe gotten up to about 6x faster, maybe. A couple extra cores in there, maybe. This was an 8-core machine, so a lot of desktop machines don't have even that many. So if anything, this is even more lopsided, this graph today. Plus, we have now ML units, right? If you pick up a Mac Studio, the ML processor on a Mac Studio itself is capable of another 20 teraflops. So you have this incredible amount of compute, which is really hard to get to directly in C++. Right? Why is that? Why don't we just throw everything up on the GPU? Well, because there's two different kinds of parallelism. There's functional parallelism, which looks like this. We're doing a bunch of things, and some can be done in parallel, and they've got branches and stuff going on. And then we have data parallelism, where we just have a whole bunch of data, and we're doing the same operation over and over and over. And it's the right side of that, which is what GPUs are just really, really good at. So the speaker notes from 10 years ago from the previous slide contains this note. Ad hoc threading, over 100 threads in Photoshop CS5, most waiting for their feature or library to be called. Right? If you launched CS5 at the time, it spun up about 100 threads. So I took a look with the current shipping Photoshop. It's much closer to about 2,000 threads right now. This is despite the fact that the team is trying really, really hard to just get everything down to one thread pool. What's our ideal? We want one thread per core so we don't overcommit the machine. Why don't you want to overcommit the machine? Because a context switch, to switch between threads at a processor level, if you count it up, is about 1 million cycles. Okay? You can do a lot with 1 million cycles. So this is a problem. Why did this happen? Stood thread. I've had this argument before. I don't think the standard should have included stood thread. I think what the standard should have included was access to a system level execution context, is what we would tell them today. I have this huge fear that Bryce's work, and Eric Niebler's work, doing the sender-receiver stuff, they're talking about, oh, we're going to have, at the system level, we're going to let you spin up your own thread pool. You'll just make a call and get a thread pool. Well, great. Now on a 20-core machine, instead of 2,000 threads, I'm going to get 20 times that amount, because everybody who was spinning up their own thread is now going to spin up their own thread pool. Okay? So please help to make our lives easier. Right? I really dislike stood async. It looks so easy to call, but what does stood async do? It spins up a thread. So let's get rid of stood async. Let's get rid of stood thread. Let's get rid of stood jthread. Now, vectorization, back to 10 years ago. For people who don't know, most of your CPUs have vectorization instructions. What does that mean? It means they can operate on multiple integers or floating point values at once, right? So kind of started with MMX on Intel processors, and then you had SSE, and now we're up to SSE like 4.2, and then Intel also has a whole line of AVX instructions. So this one went to AVX3. I think now they start naming them by width, so there's an AVX 512, which is past AVX3. It's not that they've done another 400 and some odd or 500 and some odd versions in between there. So this is incredibly powerful to get some amount of parallelism out of your CPU. What I want to be able to write is something like this, and if you saw Bryce's talk, this is similar, right? I want to be able to say something like, I'm going to take and do a transform, and what this is actually doing is blending two values. So if these were floating point values, okay, I'm taking A times alpha plus B times 1 minus the alpha and getting a new value back out. So I'm doing a transform on things. But I want to be able to do this when this is the values that I'm passing in. So what's a normalized 8 value? Well, if you're dealing with anything in graphics, right, typically what you're doing is a value of your channel, of your red component and your color, the 0 to 255, the 1 byte in that, represents a value between 0 to 1. So that's a normalized value. A value between 0 and 1 is normalized. And so you want to multiply two normalized values together. How do you do that? Well, the basic equation would be A times B plus 127 divided by 255, right? Because 255 is your 1 value. Now the problem here is that divide by 255 is very expensive. So we want to do a strength reduction to optimize that. So the actual code below the comment is how you do that. So we say we take our normalized 8, we cast it to a uint8 type. Normalized 8 here is typically an enum that's specified to have an underlying type of a uint8. I didn't put the static cast in here because they didn't fit well on the slide. So I basically strip off the little enum wrapper, I do the multiplication, I add 128. Now here's a puzzle. Why 128 and not 127? Okay. Because the rest of the math is an approximation and it's off by just a little bit, and so if you add 1 there, everything works perfectly. For 20 years, and I've been asking this question, figure out a way to derive that 1. The way I did it was wrote an exhaustive test for all possible 8-bit values, did the actual way here, did it the other way, it was off by a little bit. I said, maybe I could just raise it a little bit. I stuck a 1 there and everything worked perfectly. Great, I discovered this early on in Photoshop before, I think this is now well known, but before it was published. We thought that this was our great trade secret. This was like a 15% improvement, understanding that we could do things this way in speeding up Photoshop. And to this day, I can't derive, right, from first principles how I would come up with that 1, right? So sometimes it's just experimentation. And I've tried a bunch of different ways to do the math. So if anybody wants to take a deep walk through discrete mathematics, have a good time. Okay, so then we're going to take this temp value, we're going to add it to itself, shift it down by 8, and then we're going to shift it down by 8. So that's how I multiply 2 pixels together. That's my multiplication operation. So the problem with that is as I'm writing that code and I'm looking, what I want from that code is, back up, is if I've got this code and maybe I have a wide normalized 8 that's 8 wide and 16 and 32-bit wides, and for those operations I can use intrinsics to do this, and there's a difference as to whether I'm multiplying A and B times a single value C, so it's C times A and C times B and I want 2 values out, or whether or not I want A and B times the respective C and D. Right, those are kind of 2 different operations. I want to be able to kind of write this whole space in the vectorization space and then have my algorithm pick the correct one and spin up the vectorization unit. If I write it like this and I run it through a vectorizing compiler, I just get a bunch of non-vectorized instructions out the back. So we already talked some about why we can't put everything on the GPU, but this is still true. I think in this case, the CPUs have actually gone up a bit in ratio. But for sequential operations, a CPU is 10 plus times faster than a GPU is. So truth here, typical object-oriented paradigms of using shared references to objects break down in a massively parallel environment. Really quick. Sharing implies either they're single-threaded or that there's synchronization going on under the hood. 10 years after making this observation, many developers, I find, still don't understand this tweet. This was something I tweeted a while ago. I'll let you read it for a moment. Does everybody understand this? Yeah. This was after working with a team where they were calling all of my stuff and just absolutely everything was like, hey, make shared make shared, right? That's both how to kill performance and introduce bugs at the same time. So why is sharing and synchronization bad? This is my graph of Amdahl's law. Most of the graphs you find online I don't like because they're logarithmic on one axis and linear on the other, and that really masks what's going on. So this is looking at performance versus number of processors at the bottom, and each line going down is what happens if just 10% of your code is synchronized. Okay? So ideally, everything would scale straight up. Add more processors, go faster. Okay? Out at 16 cores, you can see what are we getting? Just a little better than 6 times performance if just 10% of our code is synchronizing. Okay? This kills you. So when I hear people say, oh yeah, I've got this shared pointer and I need to use it across threads, and somebody else says on a mailing list, oh yeah, the way I always do that is I just stick a mutex around the whole thing. Please don't. Right? Please stop. To utilize the hardware, we need to move towards functional, declarative, reactive, and value semantic programming. No raw loops. This slide is from 10 years ago. This predates my C++ seasoning talk, so I've been saying no raw loops for a long time. Why did I say no raw loops in this context? Right? Because how you structure your loop, right? If you're doing anything with SIMD or GPUs or parallelism, how you structure that loop and how you structure that algorithm, you need to peel off the stuff in front. You need to get the data aligned. You need to handle the tail end and wrap things up. You don't want to be writing that stuff all over the place, right? You want to package up all of your loop structure in one place and basically just provide the kernel, just provide the function that I want to operate across that. So no raw loops. Without addressing vectorization, GPUs, and scalable parallelism, and now we get to add MLUs to this, standard C++ is just a scripting system to get to the other 99% of the machine through other languages and libraries. Okay. This is kind of depressing. It comes across as more depressing than I mean it, because one problem here is it's typically your C++ code that's coordinating all of those other resources. And it's very easy to say, oh, well, then we'll write all of that in Python. And then I pretty much guarantee that Python will be your bottleneck in coordinating all of those other resources. Okay. So it is not as doom and gloom as I mean it to be, but maybe there's some trade-offs here, right? Maybe we can give up a little bit to get a little bit. Okay. Do we need such a complex scripting system? So truth, this is my definition of truth. The confidence a language provides that code is correct and efficient. Okay? So I hate when people say, oh, Haskell's great. I can compile my Haskell and I can say, dash, whatever it is, vectorize or thread or whatever their option is. And now my Haskell program just runs across all my cores. It's like, yeah, it does. And you probably picked up about 10 or 15%, right? Because you're relying on an optimizer within that environment to make decisions about what are your grain size, how to try to fold information in, how to structure your algorithms. And within Haskell, an algorithm that's efficient when it's parallelized and an algorithm that's inefficient when it's parallelized looks identical. Okay? And you have no guarantees around what the optimizer is going to do, so you really don't have a way to tune it. So I really, in Bryce's and Eric's and the other people working on how we do senders and receivers and parallel algorithms, I really want them to think hard about how do we write things in such a way that we guarantee that we get the vectorization. That I guarantee that if it vectorizes on x86, it will vectorize on ARM, it will vectorize within WASM. WASM has vectorization, if you're not aware, right? How do we get there? How do we get to efficient by definition, right? That's providing confidence that we have efficiency, right? And at the same time, how do we get to trust that our code is correct, right? boy, introducing mutexes into the language, my whole C++ seasoning talk, like no raw mutexes, no raw synchronization primitives. The low-level primitives we give developers now are really hard to use correctly, right? There's probably, I'll be conservative, 20 people in the industry who could really use those things well, okay? And there's probably 2 orders of magnitude, 3 orders, 4 orders of magnitude more than that using them, okay? Which brings us to goodness. What do I mean by goodness? Did you have a question, Guy? Or were you? Nope. So goodness is just the grab bag of everything else around here. So I don't have a definition of goodness. It's goodness. It's all the wonderful stuff. 10 years ago, this section of my talk was around what I coined as content ubiquity. And this was observing that within the industry that piece by piece, kind of every application domain was moving towards a model of content ubiquity, right? It used to just be on your desktop, and then it was your desktop and your phone, and then your desktop, your phone, your browser. And I used to just have my music on my CD, and then it was all my music on my iPod, and now it's all my music on whatever device I can see within my reach at any point in time. It's all my stuff everywhere, wherever I am. That's content ubiquity. So, the definition. Content ubiquity, access to all your information on all your devices all the time. So a short demo. Let me see if I can do this. Always trying to switch video in the middle of a talk. I really wish there was a nice way to set things up within Mac or Windows and just let you flip views. Flip configurations. Just put that full screen. And I will kind of recenter this. Oops. It is really hard to see on this display. Let's see, fit to screen. There we go. Okay, so this picture, I'm going to apologize a little bit. I probably shouldn't be using this picture. This is Nissan. So Nissan makes beautiful advertisements. Please go buy their cars. Now, hopefully they'll forgive me. I picked this picture because a few years back I did Photoshop for the iPad. And that was a big project. And when we did that project, since I'd already done Lightroom Mobile and Lightroom Web, and before I did both of those, I had been talking about content ubiquity and how it was get all of your information on all of your devices all of the time. And that was what had me at Google for the little year plus I was at Google. Google actually hired me. They said, we want to hire you to figure out how we put large-scale applications like Photoshop in the browser. This is Photoshop running in Edge. Sorry, I didn't use Chrome. Roughly the same image. And this image was the 4th image that we ever displayed on an iPad. So it kind of has a fond space in my heart. The first 3 were a red rectangle, a blue rectangle, and a green rectangle to make sure that we had our channels in the right order. So this was number 4. Which was pretty exciting, I have to say. So this is a professional advertisement. I got this by asking our QE department if they had an image that was real, something that a professional would create, not anything that was insane that would push Photoshop to its absolute limits, right? Not a stress test, just something real and legitimate. And this was the image they came back with. And so this image is about 10,000 pixels by 8,000 pixels. It contains about 70 layers that are 10,000 pixels by 8,000 pixels. It's got blend modes, and the layers are in groups, and kind of everything except for text in here. We do have a text tool that works like text on desktop. So, and this is inside the browser. And you can see we can zoom in here. I'm using my trackpad to just pinch. So you can get, Photoshop all the way down to the pixel grid and pan and zoom around. And it's very fluid. And this is not just a stagnant image. I could pick my move tool up here and see if I can do that with a trackpad. So that's live compositing, a whole stack of layers there at one time. Painting works. If I can grab a paintbrush, maybe target something else. I can't paint on what's targeted. Was the error message there? So, okay, so now we're doing a little painting behind, so you can see it's live compositing painting on the background. So this is the full Photoshop engine, and there's a lot more features that are in there than are even lit up in the UI, because we have this architecture where it takes us a little while to surface everything. This is about 30 million lines of C++ code compiled into WASM, okay, and running inside of an existing browser. So that's pretty cool, right? I don't know how many people know that you can do this with C++. So I wanted to show that off. So the last 10 years, this has kind of been my career, has been content ubiquity and demonstrating that this stuff is done. And this was particularly sweet for me because Google hired me to work on this problem of how do you make an application the size of Photoshop run inside the browser. And I said, I have all these great ideas about how to do it. And they said, go fix bugs on Chrome OS because we got to tape out the ROMs for the hardware manufacturers. And when you're done with that, maybe. And when I was done with that, they're like, yeah, we don't think that's worth solving. And 10 years later, I get to demonstrate that, yeah, I actually knew what I was talking about, and we could pull this off. So I wanted to show that. And it's not just me. I mean, there's a big whole team behind here now, too. Now I cannot get out of my full screen mode. Sorry, let me flip back. Okay, and we're back. So that was that. So if you want kind of more information about how this actually happened, there's this great link, so you can Google for it, bringing Adobe's Creative Cloud to the web, starting with Photoshop. This is a video that Google produced as part of Google I/O, and it goes through and kind of details both how we did it and how we changed the web in doing it. So we pushed for things like wide color gamuts and HDR support within your browser, and worked through a whole bunch of threading issues inside of WASM, and how do you get zero-cost exception handling, because Photoshop uses exception handling heavily. And just a whole number of things that went into this. And so it was a big collaboration, not just with Google, but we worked with Mozilla, and we worked with Microsoft, and we worked with Apple, and we're continuing all of those relationships to bring this forward. But I think it really demonstrates what the web is capable of. But I also have to say that that demo was created both because of C++. It was C++ that made it possible, and it also happened in some ways in spite of C++. Right? What do I mean by that? Well, as soon as you get something onto the web, what do people want to do? They want to start collaborating. They want to start coordinating things. We are downloading documents from the web. The networking, the state of networking within C++ is abysmal. It really is. There's just no better way to say it. So trying to get the same stack that's going to execute on your desktop, on your iPad, inside the browser, that's doing network-heavy stuff is really painful. That was a huge part of this project, just getting the document to the device and getting the document back up to the device, or back up to the cloud. So, this was from before again. This idea of ubiquity has gone mainstream. You know, looks quaint now. 10 years ago, a typical US household had 3 TVs, 2 PCs, and 1 smartphone. Now you can't live your life. It's like every family member has to have a smartphone. A typical US worker has access to a PC at work or is provided an email solution for communication. And you can kind of read on. It's just kind of quaint. It's amazing how far we've come with networking in 10 years. So content ubiquity has become the expectation. If you're working on something new right now, as a new product in the consumer space, you have to be thinking, how does this play on desktop? How does this play on mobile? And how does it play on web? That is just the expectation. And it's not something you can bolt on. And that makes it tough, because that's what I did, is I bolted it on. Dropbox solutions don't work particularly well. You need something that's integrated. The experience that you have on web and mobile, and luckily we did this on mobile first, you don't have a save command typically. You don't want to be saving your document and putting it aside. People switch browser tabs, and so you have to deal with, well, we're auto-saving. Well, what if somebody closes the browser tab in the middle of our save? How do we deal with that transaction, right? There is a whole bunch of complexity that goes into that. So achieving a seamless experience really requires a rethink, both around data models, how do you do incremental changes, transaction models, editor models to support partial editing, proxies and pyramids, UI models to support touch, small devices, 10-foot interfaces, all of these things. If you can make changes available to other devices, immediately your boss is going to come and say, hey, that's great, so we can work on it at the same time now, right? Right? Because collaboration just becomes the expectation, right? So sharing and collaboration are going to be your next ask. So one problem here is that getting to that top layer, right? Here, even though the main engine here is all written in C++, we've got the challenge that we have to bridge that code into Kotlin on Android, and we have to do Swift or Objective-C++ on iOS, and we have to do TypeScript to get to the browser. Luckily, managed C++ we can kind of push aside, and Windows these days is mostly just C++. But it's still a lot to deal with, so we would like a unified model. Vendor lock-in and commodity technologies only seems to slow down developments within the industry, right? Every vendor wants their own lock-in, but the net effect is everybody within the industry moves slower. And this is a problem. And this is a huge problem in GPUs right now, right? We thought that Vulkan was going to be the answer and that would provide a cross-platform stuff, but then Apple dropped Vulkan and the web went a different way. And so now if you're doing GPU stuff, you've got to support Metal and Vulkan and DirectX and CUDA, and it's just a mess. It's a painful mess. And all of those under the hood are kind of C++, but not. You can't take code from one and run it in the other place. So now what? Right? This was the end of my talk previously, and what I said is we need more simplicity and we need standardized access to modern hardware. And the modern hardware has gotten worse, right? We now have things like heterogeneous cores, and you have unified or non-unified memory models, and you have NUMA memory models, and all of those things have an impact. I was just reading an article. Intel shipped their Alder Lake CPUs, and the high-performance cores on the Alder Lake CPUs, if this article was correct, have AVX 512 SIMD instructions, but the high-efficiency cores do not. And so you have AVX 512 depending on which core your code gets scheduled on. Well, no code expects that, and so what happens? Your machine crashes. And so Intel was like, no, you have your choice. You can go into your BIOS and you can turn on, I want AVX, and turn off your efficiency cores, or you can turn off AVX and turn on your efficiency cores. That's your choice. Of course, every BIOS vendor gave you 2 independent switches. And of course you want AVX and my high efficiency cores. And then your machine, you're looking at a blue screen of death. So the fix, because Intel can't control all of the BIOS vendors, was to start fusing out the AVX 512 circuits on the chip. So you just don't have it anymore. That was wasted silicon. Okay? We need programming models that support that. We need programming models where we can say, I want to be able to execute this task, and if it's executing on something that has AVX 512, it's going to use this function, and if it gets scheduled on an efficiency core, it's going to use this function, right? And that's a runtime determination. So, same question for Act 3, and this talk doesn't have an Act 3. Now what? Right? Where do we go from here? I recently had a conversation with Alex Stepanoff. Connor actually mentioned the talk that we were talking about. Met with Alex and we went and walked his dog for a couple hours. And this video is surfaced on the web that it's a talk that Alex gave at Adobe 20 years ago now. And it's actually I was in the audience at that talk. I don't think I ever show up on the video, but I was in the audience in the talk. And it was after that talk that I met Alex in person. We had like a 3-hour conversation, and that led to Alex joining Adobe and us forming the first round of the Software Technology Lab. And in that talk, Alex paints this beautiful vision of his vision for where the STL should go, which is this both government and corporate funded library where you have all of these wonderful software components that are well specified, very efficient, universally available, and just work everywhere. And he was very disheartened. He said, I was very naive like 20 years ago when I gave that talk. And he said, it can't happen. And the reason why he gave that it can't happen was because, in his words, that what industry valued was churn, okay? What industry valued was get another release out there. And that's kind of hard to argue with when like 90% of the apps that show up on your iPhone with an update show up as, performance and stability improvements. That's like the only change they made. And if you look at like what's the hot, what's the new and updated apps on my device, and it's like all the big vendors are just listed there, and the only reason why they're on that list is because they're shipping out bug fixes every 2 weeks, and that puts them on the list, and then you're more likely to click on them and more likely to buy stuff. So there's something to his argument, but I think it's actually only a small piece of the equation. There are some more fundamental issues here. One is what Tony Van Eerd identified in his talk, which is that complecting is easy, right? It's really easy to take a piece of code, even a solid piece of code, and think, I need to make this one change. Really, I should refactor and I should do all this to do it right, but I'm just going to drop this one line in, right? Those things tend to erode your code base. Mark Hamburg, somebody who I worked with in the early days of Photoshop on Photoshop, and he had the rule on the team, and we're trying to get back to that, and we're working hard inside with ST Lab, that 60% of your engineering time, whether that's individuals are spending 100%, some individuals are spending 100% of the time, and 60% of them, or every individual is spending 60% of the time, doesn't matter, however you want to add it up. But roughly 60% of your engineering time should be spent on improving your existing code base, not adding new features. And his rationale, thank you. His rationale for it is super solid, which is it's easier to make a mess than it is to clean it up, right? If you've ever tried to clean your office or something like that, you know this, okay? So to come back into a messy piece of code that you haven't looked at and been like, oh, okay, well, this is a mess. So now I need to like fully understand it, and now I need to go reorganize it. It's harder to do that after the fact. It's harder to do it later, and it takes more effort than it did to write the code in the first place. And if you don't do that, then you will just keep accumulating technical debt. So, another reason that drives this to be aware of, and this will go work against the you should spend 60% of your engineering time improving your current code base, is what your boss is concerned with is, can we ship a better approximation to the solution than our customer can by this point in time? Okay? They don't care if it's right, they just care if it's better. So that's always going to put time pressure on that. That's always going to mean that your pressure is going the other way. Let's put 100% of our people on resources, get something that's better than the solution out into market faster, and you write horrible code. So it's those pressures that really, I think, are the reason why we can't get to Alex's vision. Now, C++ is already too complex for everyone, it's myself included. But the complexity doesn't just come from the size and the ugly syntax. Lisp and Scheme and Haskell and APL are really beautiful languages. Okay? They're very small, their definitions are small. The Haskell language report is 300 pages, which half of that's the standard library, so the language definition is 150 pages. But I don't think I've ever heard anybody say, oh, Haskell was such an easy language to learn. Okay? So these are indicators, but it's not the whole story. There's more to it than that. So a more normalized and approachable syntax would help, but I think more is required than just that, right? We need beauty, we need the truth, and we need goodness for whatever the definition of goodness is. So that is the end of my talk, but I am going to put this up here. It's been mentioned a couple times. Dave Abrahams and his collaborator Dimitri have been working on this. This is not like an announcement. They gave a keynote on it at C++ Now. Val is an academic language, and the idea with Val is how far can we push the idea of mutable value semantics within a language? Can we create a safe language can we create a safe language and have mutation within that, right? If you look at, and efficient by definition. And so if you look at the functional languages, right, they get safety by disallowing mutation, but that comes at a cost. And the big part of that cost is you're relying on efficiency by optimization. If you want efficiency by definition, we assert you need mutation. And so we're trying to see how far can we push that. The link here, if you go and look at it, the language has made just tremendous progress in the last couple of months. There's a, what is it? I want to say language recipes, but it's language overview or language guide or something like that. Yeah, linked from here, you'll find the guide, you'll find the specification. It's a nice specification that's evolving pretty quick. So if you're kind of interested in languages in a small project, we don't have a big team around it by Google. There's no fanfare here, there's no announcement. Our hope is actually that people steal ideas from this language and incorporate them into C++ or into Carbon or into someplace else. What we're trying to do is vet the idea. But it's coming along, it's getting interesting. So I just wanted to bring that up. And that is the very end of my talk.
So the story with Sean and safety is a long one. In fact, the story with Sean and me and safety is a long one.
Yeah.
And he said, something happened at the latest C++ Now, but I remember like maybe 10 years ago or more when we had this discussion at C++ Now, and you said, I'm working on this Photoshop for the web thing, and we're running C++ inside of a sandbox, and all the same problems exist. It's totally safe, but that doesn't make your code correct. And I thought, this is a good point. Maybe we've overvalued this idea of safety, right? Maybe because correctness is really what's important. And years passed. I went off to do Swift. I got kind of a different perspective about safety on Swift. And we're back at C++ now, recently. Yep. And, I'm talking to Sean about safety in programming languages. And he's like, this is just May, okay? So he's saying, I'm not sure I really can buy into that, just because I don't think we can afford it. I don't think we can afford the cost of those checks. And and then we were referred, well, I told him the story of what had happened on the Adobe C++ Guild Slack channel, right? So what was happening there? There were some people discussing some kind of undefined behavior that had come up in C++. And at some point, a senior developer said in this thread, with all seriousness, I don't know, if it was really, okay, yeah, technically it's undefined behavior. Great, Dave. Thanks for pointing that out. If it was really legitimate undefined behavior, the compiler would tell me so. Now, the reason that a lot of things in the language are undefined is because the compiler can't tell you so, right? It can't validate that your pointer is legal, right? So I told Sean this story, and I said, now do you understand why we need safety? It's because programmers don't know how to think about undefined behavior, right? Like, good programmers cannot handle this level of uncertainty. And it all goes back to the assurance that you feel that your code is correct. Like, can I satisfy a contract? If somebody, passes me something, is it going to be valid? Is it even going to be well-formed, right? So Sean's evolved a little bit. I think that we can actually afford the checks. One of the things I discovered in Swift is, actually, in the cases that matter, the optimizer really can see that you're iterating over a range that you've already checked the bounds on the end of the range, right? So most of those checks are actually affordable. And ultimately, like as an industry, for programming at scale, we can't afford to do it without safety.
Thank you, Dave. There was no question, so that was great. Yeah, take at least one question here.
It's not so much a question, but just get your thoughts on a reflection. Like, it's sort of the GPU, the amount of flops that you can get out of a GPU graph is pretty overwhelming. You see this, but I'm just sort of thinking about if I had to dispose of a tree. Like, I'm thinking about, like, and just watching a crew do that. They have this gigantic wood chipper. But there's a guy, just like one guy whose job is to throw it in there. Yeah. And a lot of the time I see it and it's not really doing anything. But there is one guy whose job is to put it in there. And it didn't seem like it was that inefficient. The tree got done. Sure. What's your thought on that? Like, I mean, we do need to have that sort of...
Yeah, that's exactly what I said, is it's your CPU that ends up coordinating everything. And even that is starting to shift, right? We're starting to see processors within your memory and processors or memory attached directly to your GPU, which we've had a long time. SSDs attached directly to your GPU so that the GPU can load directly from the SSD without going through the main CPU. But yeah, it's your CPU that's coordinating and is handling a number of tasks that just don't parallelize well. And it's interesting though, because also there's trade-offs here with efficiency, right? Like if you wanted to parallelize a find if, right? You can do that on a sequence. You cut the sequence in however many slices as you have cores. You feed it to each of them to do the find, and then you do a reduction to take the first one back out. So it's going to be a pretty trivial reduce algorithm. But if you do that, that means now that you're not on average scanning half of your list. You're scanning the entire list. Okay, so you have doubled the amount of work that you are doing on average in order to perform this operation. That probably saved you time, assuming you have more than one thread that you can parallelize across on, but it probably also cost you energy. And one reason why I couldn't put up slides around the performance of modern hardware is because you can't see the performance of the CPU separate from the GPU. Because if you run your GPU flat out, first you're going to thermal throttle at some point, and there's nothing left for the CPU on that machine, right? So on modern hardware, you're trying to live within a wattage and a thermal envelope. And right now, we kind of throw our hands up and code as if that stuff doesn't matter, but it actually does, right? If you're trying to maximize the amount of battery life on your iPhone, that matters, right? And we don't have, I don't even have any good ideas. We don't have any good ideas about how do you model that in such a way that you can manage it, or even that the operating system can manage it well for you. But that's the complex world we're trying to navigate through these days, and that's the complex world that I think C++ has to navigate through, right? I would love to see it if C++ 26 maybe had like some guaranteed level of GPU support, right? If I could write code and it said, hey, if you've got a GPU discrete or integrated, it doesn't matter, and you do this, that will execute on the GPU. That would be amazing, right? I'd like to be able to get SIMD use by writing an algorithm with a simple operation that just multiplies two numbers and not have to write a whole bunch of intrinsics to get that to work. And not hope that the compiler can see what I'm doing and optimize it accordingly, right? Maybe, hopefully. So.
Hey, so it's been a while since I've used C#, but I remember there being like an unsafe keyword, and then you'd have a block of unsafe code, like safe and unsafe in air quotes. But I don't know how something like that could be added to C++. But what do you think of that approach in a broad sense?
The approach in a broad sense, if you look, Rust has a similar thing. You have a way to decorate unsafe code, and I think Swift has a similar thing to decorate unsafe code.
We do it with naming convention.
Yeah, they do it with a naming convention. So yeah, I think the approach is valid, and the idea of having safe by default is valid, and then the ability to say no, I know that I'm satisfying the preconditions, and whether or not the compiler can see through that, just call it and go fast. On the flip side, that's at least it's easy to spot in a code review, but it's a little bit like handing people a mutex,
Right.
because there's always the person who's like, yeah, I know I'm doing it right, and I'm like, yeah, you're 2 weeks out of college. I doubt it. Right? I mean, we've all been through that. We've all been through that learning experience. So, but yeah, I think the approach is valid. So I have no idea how to get something like that into C++. C++ is sharing and reference heavy, right? We don't specify our semantics. We say, oh, pass this by reference, pass this by const reference, and we have conventions around what that means and the safety that that implies, but nothing that's guaranteed. And if you tried to put strict rules around that, I bet a whole bunch of code wouldn't even compile. So
what, including STL iterators, where STL is where our value semantics sort of originated, like where we started to realize that was important. Right. So it's really deeply embedded beyond safety. Yeah.
Is having a safe decorator an option, or like I mean there'd be trust involved in that, but anyways.
Yeah, a little bit. I mean, there's kind of an odd thing, which is const expr is kind of a safe decorator, right? If you can, if you can write something that's const expr, it's kind of not allowed to be able to touch things outside of its little scope. So, yeah, maybe.
Okay.
Hi. So I know we're talking about C++ as a language, but my question about is also about efficiency and safety, but in terms of just general software development. On our day-to-day coding, there are times that we may think that, okay, I know this code is correct and safe, I have tested it, I have written my tests and all fine, but then we may have some discussions or some thought that, am I going to add some safety guards around this code, even though I know it works now, but what if 2 years from now I am the one who's going to break it or someone else is going to break it?
Sure.
And then there's always the same question that, oh, you're going to slow down the code. So I want to know what is, if you have any guidelines in terms of like, okay, where should we draw a line?
Yeah, I tend to say assert things, at least for your debug builds. If we had contracts, I would, hopefully contracts would have the ability to assert checks. But you have to be careful to not change the complexity of the operation, right? You can't assert that your comparison is a strict weak order by matching all the pairs of values that come into it. That would change the complexity of the function, and that would take your thing down. Like Microsoft at one point shipped a secure STL, which changed the complexity of some operations from being constant to linear. And the problem is you called that in a loop, and now it went from linear to quadratic. And your program, your debug version of your build just never ended. So you can to a limited degree, and I encourage people to do that, even if it's just to get in the habit of stating what that is. Because even if you come across later and comment out that assert because you can't pay for it in your debug build, that's a comment that's like, this is the precondition, right? We're just not going to check it for you. Dave is a big proponent of every function you write should have a 2-line specification, just tight specification of the contract for that function at the start of it. And I think it's a very, it's a very valid thing. It's a hard discipline to get into, and I think it's a hard discipline to transition an organization into, but it's something we're going to try. So yeah, I mean, that proves out the thought. And, right, I have written code with an assert, and the assert is like a half a page long, and above it, it has like a half a page comment. And with all the description about why this assert is here, and why if this happens, it's a logical contradiction in the system, and blah, 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 and all the details about don't violate this, and if you did violate it, this is probably how you did violate it, and so don't do that. That's already in our code line. See this link to this page, right? Don't do it. And invariably, somebody will walk into my office and say, so I'm hitting this assert, but my code works if I just comment it out. So I'm going to do that, okay? You can't win, right? So.
Thank you.